Hello and welcome to the lecture series on reinforcement learning. My name is Alireza Modirshanechi, and this is the second part of my lecture on curiosity-driven exploration. In the first part of the lecture, we discussed how exploration bonus can help reinforcement learning in tabular setting. Particularly, we discussed multi-arm banding task and Markov decision processes, and the fact that adding an extra term to the reward signal can help collecting reward. In the second part, we focus on curiosity-driven reinforcement learning as a general term and discuss what if there was no primary reward signal? What is the influence of this exploration bonus by itself on the behavior of an agent? In the traditional reinforcement learning models, rewards are always external. This is a typical image of how an agent interacts with its environment in the traditional models of reinforcement learning. You have the agent, it sends some actions to the environment, evaluate this action, gives back some reward signal and some states. There is an alternative approach called intrinsically motivated reinforcement learning, inspired by works in psychology and neuroscience. And this approach says that reward signal is essentially internal. And the idea is that humans and animals don't have a specific and particular sensation channel for reward. They don't receive rewards by themselves. They eat food, they taste food, and based on tasting, they then feel rewarded. So the idea is that agents or animal only receives sensation from the external world and then use this sensation to extract some reward signal, feel rewarded, and make some inference about the state. And then these reward signal and states go to some classic RL agents, make some decisions that are then translated to some action to be taken in the external world. But this reward signal is interesting. We focus on this reward signal now and talk about two potential components of it. The first component is what is called extrinsic component. It includes all the traditional terms that are believed to be rewarding for humans and animals, like nutrition, like money, anything that has extrinsic value. There is also another term that people believe that is included in this reward signal, and it is called intrinsic component of it. Things like information or surprise or novelty or anything that is believed to result in curiosity-driven behavior. So when someone does something and we call that was driven by curiosity, it usually can be classified that, oh, that person did it to face something novel, understand something better, or gain some knowledge. And in this setting of having extrinsic and intrinsic components, usually the extrinsic component of reward is easy to characterize. It is given by primary needs of the agent, or in more artificial setting, it is a direct signal from the environment. But for the intrinsic component, it is a challenge to characterize it. So an important question is, how should we characterize the intrinsic reward function? In machine learning setting, this intrinsic reward function should be useful for learning complex behavior, or in task with primary reward, with extrinsic reward, be helpful for collecting the extrinsic reward like exploration bonus. And in cognitive science, neuroscience, and psychology, this intrinsic reward is important to explain curiosity-driven behavior in humans and animals. Approaches to address this question can be divided into two groups. The first group is what I call bottom-up views. These methods start directly from the question of what are we curious about and characterize the reward function based on experimental observation and heuristic reasoning. For example, we say that, oh, animals are interested in novelty, hence this reward signal should include some terms related to novelty. or we think that an artificial agent is better to learn a good model of the environment. So we can encourage this agent to go and search the part of the environment that is most uncertain about and learn a better model of the world. So the reward function should include some parts related to uncertainty. The other approach is a top-down approach, and it starts from what are we curious about. So it doesn't characterize reward by itself, it characterizes a goal for a population of agents usually, and then define reward as some local proxy of achieving that population level performance measure. My focus today is mainly on this first group. I'm going to talk a bit later on this. But here, to make it clear, it's a very elegant approach. To make it more clear, I'm just going to give an overview of one example in the field taken from this paper that I cited on the previous slide. The idea is that we have a population of agents. Each of them is interacting with the environment by receiving state and giving back action to the environment, and at each point receive some reward signal which is function of the local observation, so S1 and A1, things that the agent has access at time. But then it goes on until it dies at time capital T. Given all these agents together, we can have some fitness measure which is for a whole population over a time course. And this fitness measure, for example, measure the survival rate of the species or reproduction rate of the species. And this fitness measure is received by evolution, and evolution improve the reward function by maximizing this fitness measure and give back the reward function to the population. And now we have a new improved population with a new reward function, and they interact with an environment, the same environment as before, but with a new reward function, and go on. And the idea is that over the course of few generations and few generations of population of agents, this reward function gets improved, and it acts as some proxy of this population level fitness measure. So the reward function is computed here locally, and the agent only cares about this local reward, but by seeking this local reward in a very implicit and indirect way, the agent is maximizing the fitness measure of the whole population. And this can be linked to curiosity by thinking that, oh, probably over time it was better for agents or humans and animals to make a, for example, model of their environment. So curiosity helped them to do so, and at the end of the day, that helped them to survive with a higher probability. But as I said, I just want to briefly discuss this, and I'm going to mainly focus today on these bottom-up views and directly characterizing the reward function. There are many candidates for intrinsic reward signals in the bottom-up views. Here I discuss three groups of this reward signal. The first group is a state novelty. It measures how infrequent the state is at time t+1 or at time t. Here, what is written on the left says that novelty of going to state st+1 after taking action at at state st. As we have seen in the lecture of surprise and novelty, novelty does not depend on the previous state and previous action, but only on the landing states, which here is st+1. And is a decreasing function of the frequency of state st+1 until time t. A naive definition for this can be t of time t st+1 divided by t. Is how many time, what is the fraction of time that the agent spent at state st+1. And this term here just saying that novelty is a logarithmically decreasing function of the state frequency. Another approach is to just say that is not a function of frequency, but only the count of how many times state st plus 1 has been observed until time t. Another group of candidates for the intrinsic reward signal are transition surprise. Transition surprise is assigned to transition from state st and action at to state st plus 1, and has a very similar form to this state frequency, but it is conditioned on st and at. This term is basically the estimation of the true transition probability of the Markov decision process. And the minus logarithms is basically that the less likely transitions are more surprising. This term here is also known as surprisal or Shannon surprise. I will discuss a bit more about transition surprise in the third part of the class. Another group of candidates for the intrinsic reward signals are information gain or progress rate. Basically, here what you see on the right side, you see the estimate of transition probability for state action st and at at time t plus 1. So after the agent experience this transition, it updates its world model, the estimation of the transition, into this p of t plus 1. And here on the left side, you see the same distribution, but at time t. And d is just any distance measure. I will discuss it more in the third part of the class, but you can consider Kullback-Leibler divergence or total variation distance, any distance measure that you would like. And then this term quantify how much going to state st plus 1 after taking action at state st improves or changes the model of the world of the agents. And it has a very close link to the classic exploration bonuses of the form 1 over t for state action pairs. So to summarize just these three groups, using state novelty for intrinsic reward motivates agents to go to the states that has been observed only rarely in time. Using transition surprise as intrinsic reward motivate agents to go to the part of the environment where transitions are not unpredictable. And seeking information gain or using information gain as intrinsic reward encourages agents to go to the part of the environment where it can learn most. There are also other types of intrinsic reward in the tabular setting and non-tabular setting, like empowerment, that I'm not going to cover today, but if you're interested, I would highly recommend you to go and check them out. So all these definitions that I showed here are to some extent based on counts and how many times you have seen this or how many times you experienced that. There is a big challenge in using these quantities in deep reinforcement learning because the state space and also action space are very high dimensional. And as soon as you have a very high dimensional state space, probably every state is observed only once in the whole life of the agent. And if every state is observed only once, all states are pretty novel, so you don't see much of a difference. And there has been tons of works on defining, fine-tuning, and using intrinsic rewards in deep reinforcement learning. But today, I cover only 3 examples and say that how these definitions can be used and can be modified to be compatible for these very high-dimensional state spaces and help deep reinforcement learning algorithms. But if you're interested, you can check these 3 reviews. These 2 are on arXiv, and this one has been recently published in Information Fusion. They're very good reviews. They cover many different intrinsic rewards and their applications, how they link to each other. I really recommend it. But for now, let's move to one of the examples. The first example is for novelty seeking in deep reinforcement learning. The paper was published in NeurIPS 2016. It has already more than 1,000 citations. It's now considered as one of the classics of reinforcement, intrinsic motivation, deep reinforcement learning. And as far as I know, is actually the first one in the field that used intrinsic motivation in deep reinforcement learning. The idea is that they use a parameterized model to define and learn these state frequency. So on the pixel space. So as we discussed before, in this very high dimensional state space, counting doesn't make sense anymore. So when you see one state, this state influences the novelty of any other state that is similar to that. So they use the pixel space and learn a density, what they call density model, for the frequency of this, how likely is to go to these different states. For the sake of simplicity, you can think about it as a Gaussian distribution on the space of images. Then they define pseudo counts instead of counts based on this density model. It's very interesting because we usually first use the counts and then go to the density models and state frequency. But here is a bit different because now you are in this very high dimensional, one can interpret this as a continuous state space, and they first define a parameterized P and then use this parameterized P to define T hat or pseudo counts. And now what they do is that they use a double DQN, deep Q learning network with a reward value defined as the sum of extrinsic reward plus some small constant times something that is very similar to the exploration bonus in the classic models. But importantly, the main difference is that this does not depend on AT+1. That's why we interpret it as a novelty signal. So using this, by this combination, they use this double DQN model in 5 Atari games that they consider as Atari games with very difficult exploration part. And in these graphs, on the x-axis, you see millions of training frame. On the y-axis, you see the score. The black one is vanilla DQN. The red one is the optimistic initialization, the DQN with optimistic initialization, and the green one is double DQN with using this reward function. And as you can see, it is always better than its alternatives. And it's kind of a cool result that, you could define some parametric density models on this pixel space, use it to define counts, and then use it as an intrinsic reward, and it helps you to solve difficult exploration tasks. In particular, this game of Montezuma Revenge is known as one of the most difficult Atari game for with regard to exploration. There are 20 rooms in the environment, if I'm not mistaken with the numbers, but yeah, there are some rooms that the agent should go through, explore them, use different items here and there, and here you see they visualize the known world of the agent. On the left here, you see the agent without any bonus, and it could see through time only the main room and one extra room. But while we add the bonus, we add the novelty signal to the reward signal, what happens is that the agent can explore way more and see way more number of room in the environment. So to summarize, Novelty-seeking in Atari games enables efficient exploration and results in higher extrinsic reward. The second example of intrinsically motivated deep reinforcement learning that we discuss is on surprise seeking, and use surprise as the intrinsic motivation. It is from this paper of Deepak Pathak and colleague in ICML 2017. It already has more than 2,000 citations, is considered as one of the classic in intrinsically motivated deep reinforcement learning. I'm going to show you on this slide the block diagram of the model and go through each module step by step. The agent receives state ST from the environment, use its policy pi to take action AT. Action AT is passed to the environment, and the environment gives back state ST plus 1. State ST, state plus 1, and action AT are then given to this intrinsic curiosity module, which use these three variable to compute RT of I, which is intrinsic reward value at time t. Then this intrinsic reward value is combined with extrinsic reward value and used with A3C to learn the policy for the next actions. The intrinsic curiosity module has many different components for transforming these three different variables into the intrinsic reward value. First, we focus on this part, which is the state representation part. State T and state ST plus 1 are usually, for example, for Atari game in a pixel space in very high dimensional space. These two modules that are called featured, they transform the state from the pixel space to some low dimensional representational space that are features of these pixel space that are low dimension. Now the agent use this low dimensional representation of state ST with the action that is taken to predict with this forward model to predict the next state in the hidden representation space. So the goal of the agent is to say that, okay, I took action AT at state ST, what state I will be in next time step. And the whole forward model and the features are trained end to end by minimizing the mean square error between the predicted latent representation of next state and the true latent representation of the next state. The problem with this approach so far, if one wants to train these features, the neural network for phi and neural network for phi hat, the naive training results in what people call representational collapse, because minimizing a trivial solution to minimizing this loss is to put always this equal to 0 and this equal to 0 or any other constant. And as soon as you put these two equal to 0, this loss is always 0 independently of which state you are in and which action you have taken. To solve this issue, one needs to put some regularization for this feature space. The regularization in ICM is done by this what is called inverse model. It's a smart idea. The idea is that the agent wants to look at the next state and the previous state and infer what action it has taken. And if we map everything, if we collapse representation and all the states are mapped to the same point, then we cannot infer the previous action. So using this inverse model, training of, if we use this inverse model and combine the loss of inverse model with the forward model, then we avoid representational collapse and we can learn a meaningful representational space. Then, using prediction of the next states and the actual next states, the agent can compute some sort of prediction error or surprise, which is here the squared second norm of difference between phi hat and phi. So the more accurate your prediction, the less rewarding the transition. The funny thing is that this squared difference is actually proportional if P of t is Gaussian with the covariance matrix proportional to identity matrix, is proportional to Shannon surprise or surprisal of this transition. Importantly, something that is interesting to note is that the agents use this error function here, the error between the prediction and the observation, to train its policy and explore the environment, while the forward model is learned actually to minimize this error. So over time, the agent gets better and better by predicting next states, while it explores the environment to the part that its forward model and forward model is still not good enough to predict the next states. So the agent is encouraged to go to the part of the environment where the next state is unpredictable or less predictable, while by doing so it improves its forward model. The authors used their ICM algorithm with A3C in multiple tasks, including Atari games and 3D navigation in a maze, and show that even in the absence of reward, one can show behaviors that, by seeking surprise, that maybe we can call intelligent. You can see a summary of the results in this YouTube video. It's a 2-minute video that I'm not going to show here, but it's very nice, very interesting. But basically what it shows is that seeking surprise enables agents to learn the task in the absence of any extrinsic reward. And additionally, seeking surprise enables learning skills that are generalizable to other tasks. I'm going now to discuss a bit more the second point and later on go back to the first point. Let's look at the task where they make this conclusion that seeking surprise enables learning exploration strategies that are useful in other environments. The task is navigation in such a maze. Here you see the map of the maze from top. The agent moves here. At each point it sees the image of the environment around it. And the starting point in this slide, I'm going to focus on this starting point here, which is called very sparse reward, because the goal state is here. The agents start from here, and it should go around to find the goal state at some point and receive reward. And until finding the goal state, there is no reward in the environment. What they observe is that in this curve, on the x-axis you see millions of frames of training, on the y-axis you see average extrinsic reward per episode. The first curve, the blue curve, is A3C, vanilla A3C, without any intrinsic reward. As you can see, it never can find the goal state. It always has a 0 extrinsic reward per episode. In green, because it never can find the goal state. In green, you see ICM with A3C in the pixel space. So it doesn't map the state into the features. It does the forward model on the pixel space and then compute the difference between the prediction and the observation in the pixel space. Again, we see that it cannot find the goal state. It's always 0. So this smart idea of having the inverse model to learn the action, to infer the action that made us go from one state to another, let us make a representation space that is useful for exploration and learning. And and that's actually in orange, where you can see that around 6 million steps the agent find the goal and realize that it can go to the goal state very robustly, and that means that the agent every time around here in around 60 to 70% of time go directly to the goal state. Now they wanted to see if surprise seeking can help generalization. So if the agents, what they do here is that what they call train map scenario. This is another environment, different map from the test environment, also different wallpaper. So when the agent move around, it is the walls that have different colors and texture from the one that is going to see in these environments. They train the agent in this environment starting from here just by surprise seeking. So the agent go around and seek surprise in this environment. Now we see updated curve here. Let's first look at the scratch one. These two curves here, the one that is written scratch ICM with A3C in the pixel space and ICM with A3C with inverse model, is this one, and the green one here. These two are the curves that I showed also in the previous curve, and they are when the agent start in the test map from scratch and use a combination of intrinsic and extrinsic reward to find the goal state. These two other curves that are called fine-tuned, they do the same as the scratch one, but the networks are initialized at the end of training here. So the agents move here by surprise seeking without any extrinsic reward, train its network, and now the train network is used for this start position, and the agent start from that. Still, pixel space does not help, it's always at 0, but the full ICM model with the inverse model, it can now learn much faster around 2.5 after 2.5 million millions frame of training. It can find the goal state and robustly go to the goal state, and actually at some point after 10 million step, always 100% of time go from here directly to the goal state, which is pretty interesting and intuitive that seeking surprise, seeking some intrinsic reward help the agent learn skills that are usable in different environments, and that's kind of is consistent with the overall intuition of us about curiosity, that it helps us to do things in some environments without a particular or specific reward, which can be used later on for some reward. So that was about using surprise seeking for learning complex skills that are useful for future. Here I look at a follow-up of ICM in ICLR 2019. They apply ICM on 54 Atari games for learning with no extrinsic rewards. So here what you see, each of these panels is one of one Atari game. On the y-axis you see the extrinsic reward, on the x-axis you see millions frames of training. They apply Atari game, they apply ICM with different way to learn the representation space. This is pure pixel. This one is the inverse dynamic feature, the one that I explained. I'm not going to talk about VAE features, but random CNN features is just a randomly initialized convolutional neural network and random representation. Interestingly enough, the agent in these curves is not receiving any information about extrinsic reward, is only seeking surprise. And by simply seeking surprise, the agent can increase a lot of reward value. So it can learn how to do the task, which is Very interesting, and raising this question that is it a feature of surprise seeking or Atari games that only by seeking surprise one can collect lots of extrinsic rewards? I will go back to this discussion in a few slides. But one interesting fact is that we saw inverse dynamics in the few slides ago in ICM, and a comparison with the pixel space, and we saw pixel space was worse. We see the same results here, that pixel space, the pink one, is worse than all the other representation. But a surprising finding of this paper of Buddha et al. In 2019 was that just random feature without learning anything. So the feature model, the representation model is not learned, is just randomly initialized, and only the forward model is learned, and the policy. It performs pretty good. It has sometimes even better than the inverse dynamic model. So, time for our intermediate summary. Reward can be seen as an internal signal consisting of an extrinsic and an intrinsic component, which is simply going beyond the idea of traditional reinforcement learning, that reward is given externally by the environment. In this framework, then we can define intrinsic rewards, and we saw seeking surprise and novelty as intrinsic rewards can lead to 1. Efficient exploration for finding sources of extrinsic rewards, and self-supervised learning of complex behavior in the absence of, even in the absence of rewards. Where this we saw in the Atari games for surprise seeking, and this we saw in the, again, Atari games for novelty seeking, and for navigation in a maze for surprise seeking. So far, great. We saw that surprise seeking and novelty seeking are fascinating in Atari games and in navigation in mazes, and help collecting extrinsic rewards. So it is insanely cool and fascinating. But there's a big question, that why does seeking surprise or novelty help collecting extrinsic rewards? It's very non-trivial, and it is not clear that what is the relation between surprise and extrinsic reward in Atari games that allow agents to collect extrinsic reward only by seeking surprise. To gain some intuition about this question, let us consider exercise 2 of week 12. There you were supposed to analyze this environment where we had these n states here. Let's call them progressing state. We had this single state here. Let's call it a trap state. And we had a goal state here. And the goal of the agent is to go to the goal state and receive a reward. At each of these progressing states, the agent has 2 actions, and one of these actions take the agent 1 step closer to the goal state, and one of the actions take it to the trap state. And when it is in the trap state, one action keep the agent at the trap state, and one action take it to the state 1, so it can keep going towards the goal state. The question in the exercise was that how fast can we find the goal state in these environments? And if you have checked the solution or solved the exercise yourself, you have seen that random exploration, if the agent used random exploration choosing action A prime with probability 1/2 and action A with probability 1/2, then on average the number of action is exponential with respect to n. So if n is big, it's just a huge number. Its setting is very similar to the case of very sparse reward in the navigation in the maze that we saw for ICM in the deep learning case. However, in the exercise, we saw that a very simple and naive novelty seeking can transfer this average of exponential in n to a worst case of n squared. So here it was, for big N is almost impossible to find the goal state with random exploration, while suddenly by novelty seeking the agent can find the goal state pretty fast. And as you saw in the class on novelty seeking in humans, we did similar experiments with human participants, and actually we saw that novelty seeking explained their behavior much better than random exploration. So in this environment that you analyzed in the exercise, it seems like that novelty seeking is really magical. But what if we make a small change in this environment? And the small change in the environment is to transform the goal state into a terminal state with the reward of -1, and add a goal state here, which is super unlikely to go to, with probability very small, and then otherwise action A with a high probability go back to 0. What would be the optimal exploration strategy in this environment? And as it obviously look like, novelty seeking is only harmful here, because novelty seeking push you to go towards this terminal state that has a reward of -1. And the best thing that here you could do is actually stay in this trap state and keep taking action A with the hope of at some point ending up in the goal state G. However, we don't know in which environment we are, and we don't know what should we do. You know, in one case, novelty seeking is great. In one case, novelty seeking is only harmful. And this is simply another aspect of no free lunch idea. And that, yeah, you cannot have one strategy that is always helpful. Here, in this first setting, novelty seeking was perfect, and this other setting, novelty seeking is only harmful. A fun fact is that rats actually approach novel objects in familiar environments, but avoid these novel objects in unfamiliar environments. So when they're in familiar environments, they feel a bit safe, and they think that, oh, okay, probably novelty seeking is good, maybe more in this situation, but when they are in the new environments and unfamiliar environments, they may feel unsafe, and maybe in this setting that, oh, okay, there is some risk for novelty seeking. So whether seeking an intrinsic reward is good or not depends on the problem. So I want to claim that the fact that surprise seeking help agents collect extrinsic reward in Atari games tell us equally about Atari games that tell us about surprise seeking. That surprise seeking is particularly good for Atari games. Now, back to the overview of two approaches to modeling curiosity and characterizing the reward function. What we saw so far was for this, analyzing novelty and surprise and two possible reward signal. And the conclusion is basically whether seeking a specific choice of reward signal is useful or not is not clear in advance. So we should use something, and then in neuroscience and cognitive science, fit it to behavior of animal and see if it help explaining data, and in machine learning we should run it and check if it helps exploration. On the other hand, the top-down approach really starts with this question of, okay, let's not define the reward signal by a heuristic, but make it useful, make it useful by definition. I'm not going to discuss it, but I really encourage you to check out this example of meta-learning of reward signal. There is this very nice paper in 2010 that is related to this. Actually, this example of evolutionary reinforcement learning is taken from that. And these two more modern examples using deep neural networks. So before summarizing the section and finishing the lecture, it's time for a quiz. First question: seeking surprise enables solving some task without knowing the task true objective. It is correct. As we have seen in many Atari games, just by seeking surprise, the agent can collect lots of extrinsic rewards. Novelty quantifies the infrequency of states, whereas surprise quantifies the unexpectedness of transitions. Is again correct. That was the main separation between novelty and surprise. And the first example that we saw, that the agent wanted to seek states that are less, that has been less observed compared to the second example that we saw, that the agent wanted to go to the part of the environment with least predictable transition. Question 3. It is always better to have a component in the model for seeking intrinsic rewards. And this is wrong simply because there is no free lunch. And there are situations that seeking an intrinsic reward can be harmful. And finally, intrinsic rewards and exploration bonuses are two sides of the same coin. This is, I would like to phrase it as a thought-provoking statement that is neither correct nor wrong. They are very similar. Intrinsic rewards and exploration bonuses are very similar in a sense that they both can help exploration, but helping exploration is not the only goal of an intrinsic reward. Intrinsic reward can be used in the absence of any extrinsic reward and help exploration in general and lead to some intelligent behavior in the absence of reward. So, summary, reward can be seen as an internal signal consisting of an extrinsic and an intrinsic component. Seeking surprise and novelty as intrinsic rewards can lead to 1. Efficient exploration for finding sources of extrinsic rewards, and 2. Self-supervised learning of complex behavior in the absence of rewards. However, what intrinsic reward signal is good depends on the set of tasks we are interested in. And it looks like that surprise and novelty are good intrinsic rewards for many tasks we are interested in, including Atari games and exploration in mazes. With this, we are done with the second part of the class on curiosity-driven exploration. We discussed the framework of intrinsically motivated reinforcement learning and discussed that, okay, we can have intelligent behavior in the absence of any reward. Then we discussed surprise and novelty in reinforcement learning and deep reinforcement learning. For the information gain, we will discuss it more and see the example in the third part. And at the end, we mentioned that it is possible to have meta-learning of the reward function, but we didn't go into the detail.